Everybody, good afternoon, happy Wednesday. So now we have our class just as expected. So Monday was not Monday, sorry. Today's Thursday. What am I talking about? Wow. I've been really off this semester. So happy Thursday, everybody. So on Tuesday, I had the faculty senate meeting that I had to attend. So hopefully the video did help you. I could do a little recap of that just slightly, but of course, if you have any questions, on anything from that recorded video from Tuesday, then of course you can also ask it here on WebEx. So that's that. I also have a new assignment posted, so I'm going to go ahead and just talk about that first, I suppose. Then I'll go in and do a little recap from last time's stuff, and then go over new material. So let's begin the screen share. All right, so assignment 3 I posted it up recently, so let's take a look. Here it is. It's on the other screen, so let's move it over here. All right. So nothing too bad in this assignment. So there's a few, questions you have to sort of, think about how to work them out. But for the most part, it's really stuff that I covered in class. So question one is you want to multiply these two numbers, a and b, using divide and conquer. And then the method that gave us that n up to the log 2 of 3, that n of 1.58, that's actually the Karatsuba method, and you want to apply that algorithm. So not the straight normal method I went over. So I went over the divide and conquer approach, which was, remember, we did 4 multiplications and each took linear time to combine together. But then there was this alternative way where we did 3 multiplications. I didn't cover it in class, but I guess it's really based very much on what I did in class, which was the regular non sort of not the very nice way of doing it. It still ended up being n squared, remember? So use that alternative approach where you do 1 multiplication in that middle term instead of 2. So apply that method on question 1 to multiply these two numbers out. So not a very big input case. They're both 4 digits, so shouldn't have too much level of recursion, so it shouldn't be anything too bad. So use that enhanced divide and conquer on question 1. Then question 2, we have these two 4x4 matrices, A and B, and you want to multiply them using Strasson's algorithm. So again, I covered the basic method of that, the basic divide and conquer method. Remember, we had to do 8 multiplications at each recursive step to compute each sort of individual component of the final resulting matrix. But then, of course, we had this very overcomplicated Strasson's algorithm, which would only require us to do 7 multiplications or 7 recursive calls. So using that really big formula, just go ahead and work this one out. So it'll be a little time consuming, but nothing really hard, just time consuming, I guess. So this is actually good practice because probably for the midterm, I'll have us do stuff like this. And of course, midterm would be kind of open notes, I guess, right? Since I can't really enforce non-open notes. Now, even if the exam wasn't open notes, I would probably give you the formula for Strasson's algorithm on the exam PDF or exam write-up. I mean, it'd be very cruel to not do that. So anyway, kind of busy work, but not really terrible, just busy work essentially. And of course, for question 1 and 2, you can very easily verify if you did correctly. You can just go ahead and just for question 1, just plug into a calculator, get the answers, so you know that's your target. So if you're doing this method, you don't get that answer, well, you made a mistake somewhere. Very simple to check yourself for possible errors. Question 2, same idea. You can, there's actually online matrix multiplications, online apps for this. You can just plug in A and B and get the C matrix, and you know what the target result has to be. Very simple. So just very time consuming, but nothing too bad. So question 1 and 2, 40 easy points. So shouldn't be anything too bad. Question 3, well, you want to use that selection algorithm to find the median of this list. I'll just recap it a little bit after I cover this assignment, but really the 25 element array, and there's no duplicates. So find the median of this list, so 13th biggest element using this selection algorithm. And once again, very easy to verify if you're correct. Let's go ahead and sort this array. You can, either write a program where there are online sorters to sort it and pick the 13th element so you can verify if you correctly did it. So Again, a little time consuming, but nothing too bad. Actually, I don't even know. Maybe the very first instance, it'll give you the 13th biggest. I haven't actually, I just sort of randomly created this list and I'm going to work the question out this weekend. So maybe this could be a very good case where on the in the video I did, I had to actually had to recurse on the two sides. So hopefully if we do this selection problem, um, after one partition, it's not going to find a median. If it does, well, then I guess we were lucky. It's a simple question then, but we'll see. But it's a random array, nothing fancy. There's no duplicates, so use that selection algorithm to find a median. So that's that. So questions one through three shouldn't be nothing surprising. Just busy work. That's it. Yeah, I'll go ahead and end Discord. All right. So for question four, this one's a little bit of, you have to think about this one. So you're given two sorted lists, one of size n, one of size m. And you want to give an O of log n plus log m time algorithm for finding the kth smallest element in a union of the two lists. So this is actually very similar to the problem we want to find a median of two sorted lists. So if you have two sorted lists and you were to combine them together, you want to find this median of that combined list of these two sorted lists together in O of log n time. This is very similar to that, but a little bit different. So it's kind of like the selection problem a little bit, and similar to that, finding the median of two sorted lists. So go ahead and just um, so go ahead and just sort of give a pseudocode. You don't have to actually, write the actual code and like you can just sort of give the ID. You can draw pictures and you don't have to actually go down to nitty gritty and actually have the actual indices computed. Just give me an idea, a rough sort of sketch of how you would solve this problem. So having some pictures in there is always a very, I mean, a picture does sort of, what's the actual phrase? A picture uh, says 1,000 words, I guess. Is that what it? I think that's a phrase like that. So you like when having a picture is always kind of nice. So have a picture, have some writing, just give me an idea, sketch it out. So that's question four. Then question five. So we are, still on this divide and conquer type. Well, at least this assignment is based on divide and conquer type content. So we have these three algorithms, A, B, and C, and it kind of illustrates this divide and conquer part. So you'd have to, of course, create a recurrence relation. That would be the simplest way, and then solve the recurrence, and then pick which one is the best runtime. So just practicing with taking a word problem-ish, or somewhat of a word type problem, and creating a recurrence relation out of it, and then solve the recurrence. And in question six, this is actually a pretty simple one. You have an array of n elements, and you want to eliminate duplicates. So go ahead and describe a method that will, in O of n log n time, remove duplicates from the array. So that's pretty much it. So this homework will be due next Friday, and there's no sort of you can't submit it late, so it's due Friday, and there's no grace period because I don't think you really need one. I mean, this one is takes a little bit of time, but this shouldn't be an issue where you need 3 weeks to work on it. It's not too bad on things. So that's kind of the nice thing about a non-coding class. At least there's no stress on assignments and no stress for the instructor to have to answer last minute questions like for coding classes. So this is kind of nice to have for 77. Actually, I don't mind my coding classes, but it is nice to not have students stressing at the last second on stuff. It is nice for everybody. So that's that. And of course, as always, you can scan your assignment on paper. You can use like a writing pad of some sort, an iPad, whatever, to write this out. Make sure you submit it in a PDF form with multiple pages so it's easy for the grader to go through them. So just like for the last two assignments, same idea. So anyway, that's assignment three. So any questions on that? Just close this, but if you have a question for us, I can bring it back up. So anyway, just to sort of recap a little bit from the last time's video, just a small recap. So we had this selection problem that was mostly used to find sort of the kth smallest or kth biggest element in the list, and typically it's used for finding a median. And what we're trying to do is you want to pick some pivot, which is a median of medians, which is going to give us a favorable result. We want to basically partition a list with that median of medians. And remember what partitioning does. It breaks the list into two pieces, and the pivot value, we know exactly where it's going to go in that potential sorted list. So then we have to sort of pick one side or the other. We don't have to sort the entire list to know the median because partition is going to always put that pivot in its correct sorted position. So because of that, you don't have to have the whole list sorted to know where that pivot would have to go in the potential sorted list. That's sort of the idea for this. And of course, we always pick one side, and of course, in the worst possible case, we can only eliminate just these blue elements or red elements in the worst case, which is going to be exactly 3n over 10 elements in the worst case get eliminated. So we have the following recurrence relation. So we have this n over 5 part, which will find our median of medians. We partition, and then we pick one side. In the worst case, there'll be 70% of the elements on one side, and this recurrence actually does give us theta of n. Actually, I think it's like roughly 10n, but 10 is a relatively small constant compared to the size of n. So that's the selection problem. So in the video, I sort of went over this. So that's really about it. So of course, if you use this selection algorithm to find a median, then we can guarantee quicksort to be n log n. So that's why quicksort is really kind of regarded unofficially to be n log n, because it's very easy to avoid that n squared. And also, practically, it's very unlikely statistically to always have the worst case scenario. But then here, we guarantee that the worst case n squared can never even happen. And we can just use this O of n time selection problem, which is really nice. So quicksort is kind of solved, I guess, if you will. Kind of, that's that. So now I want to go ahead and just sort of go over just, sorting, or just the conclusion of sorting. So the first thing I want to do is go over sort of an honorary mention to other sorting algorithms. It's kind of like the Watch Mojo videos where I'm going to go over the top sorting algorithms. And of course, here's honorary mentions coming up. So, of course, we have, insertion sort. And remember, it's an O of n squared time algorithm. So in the worst case, it's O of n squared. But of course, it has some scenarios where it can be O of n. There are situations where it can be O of n in sort of the best case. So it's the best case scenario, it can be O of n. And of course, in the average and worst case, it's going to be n squared. So I'm not going to discuss that in so much detail in this class because hopefully in CS 302 you were exposed to this algorithm. So anyway, we know that's O of n squared, but it has this sort of potential O of n time in the best case. But really, it's not really always O of n. It's very rare for that to happen. Now, of course, I'll just go over a few other ones here. So bubble sort. This one only has, I think Dr. Lorimer once said this, that the only benefit of bubble sort has a very nice and cute name, bubble sort. But it's not really such a great algorithm. But of course, again, it's O of n squared in the average and worst case. So I always call this a jury duty sort, because if you're in jury duty, if you're ever unlucky to have to go there, at some point you have to sort of sort yourselves among jury IDs. And often you get into line, you check the person behind you. If they have a smaller ID, you just swap with them. And you keep doing this again and again. That's how bubble sort works. Now, bubble sort can be O of n as well. But you have to sort of write the code to have this Boolean flag, which means that if after one pass of the inner loop of bubble sort, if no swaps happen at all, then you know for sure it has to be sorted. So you can stop right there. So initially, if you do one pass of bubble sort of the inner loop and no swaps happen at all, you can stop, because that means there won't ever be any swaps ever again, which means the list has to be sorted. So you can update bubble sort, you can modify it to actually be sort of O of n in the best case if you have it sort of modified. But insertion sort will be O of n without modifying if it's already sorted or if you have a special case. Then we have selection sort, it really seems to be O of n squared no matter what, really. There's kind of no situation where it can be better because it's a very not so interesting sort. You just sort of pick, you find the biggest element and you put it to the end. Then you go ahead and find the next biggest element, put it to the end. So you do this O of n work n number of times, it's n squared. So there's really nothing you can do to make this actually better. So now, of course, we'll go over heap sort later on in this semester, but it's an n log n time algorithm. And we covered also, I guess we didn't really cover merge sort in this class. I'll just go ahead and I'll just highlight this one as well. So you may have to kind of, read up on these a little bit if you forgot. I don't want to spend too much time in class on these. So yeah, go ahead and read up on these. Now I feel like an actual college professor saying that, all right, students, go ahead and read up on pages 1 and, but mostly you just kind of go through all these, but merge sort's pretty simple. It's O of n log n all the time. So we have this. And of course, quick sort is, I guess I haven't covered heap sort in this class just yet, but I do plan on going over binary heaps and of course binomial heaps. Then I'll cover heap sort, I guess, since it makes sense to cover it at that time. But anyway, I'll leave that part blank. But let's go over quick sort. So it's just highlight this as well. So it's really O of n log n in the average and best case, but it has that very rare O of n squared in the worst case. So we have several sorting algorithms sort of defined here. And I'm guessing you probably have to learn all of these, or at least most of these. I mean, I don't cover bubble sort or section sort in 302, but I do cover insertion sort, merge sort, and quick sort in 302. So I'm guessing you probably have to have covered that in your 302 sections as well. So, okay, so now we have these different sorting algorithms. And we're noticing that, well, we're seeing O of n squared, O of n log n. So I guess one question is, well, what is the best one? Well, obviously the best one is n log n, but the question is that n log n really the best we can possibly do? Is sort of the question here. So let's go ahead and go over a lower bound for comparison based sorting. So, okay, so for one, what's comparison-based sorting even mean? Well, so far, I mean, I'm not sure if you've covered other types of sorts in your 302 class, but the ones I sort of highlighted above, right here, these are all comparison-based sorting, all of these. And basically, it really means that we're sort of comparing any two elements in the list, and then of course we swap or we don't swap based on that. So we're always comparing any two elements, basically. That's sort of the idea for comparison-based sorting. So basically all comparison-based sorting is, so just write this out, comparison-based sorting, we simply just always compare any two elements in the list. And then we go ahead and of course we swap, we don't swap based on that, but that's a comparison-based sorting. So a lower bound for this really means the following. So a lower bound for this problem implies that lower bound implies that in the worst case, we cannot do less amount of steps than, I suppose, f of n. So a lower bound would imply something like this. We're going to have omega f of n. So fn is some function, some growing function, with respect to n. And omega really means that in the worst case, we have to at least do f of n number of steps. Put this here. So other words, we must perform at least f of n steps. So, you know, big O, big theta, and big omega, it doesn't really mean big O is worst case, omega is best case, theta is average case. It really means that big O means in the worst case at most, omega means in the worst case at least. So you want to go ahead and see what is that lower bound for any comparison-based sorting. So to show this, we're going to have to use a decision tree to help us see what's going on. So we're going to right now try to create the best possible comparison-based sorting that could possibly exist. Now, this sorting algorithm is maybe even more efficient than merge sort and quick sort in its average case. It's something that's the most efficient that could possibly exist. Maybe we haven't even discovered it, but this one is the best we can, definitely do, I guess is the right idea. So we're going to have the following situation. I'm going to have three elements in a hypothetical list. So A1, A1, A2, and A3. We have these three elements in our list. So let me go ahead and just keep it like this. So for any comparison-based sorting, we're going to have to compare two elements in this list. Let's go ahead and compare A1, A2 first. So we're going to have this branch over here. We compare A1 if it's less than A2. So we'll assume for right now the values will be all distinct. I mean, there will be no duplicates in this array of size 3. So in this case, if that's the situation, then we have A1, A2, and A3 in this order. So we're going to sort of have this sorted in ascending order. Now likewise, if let's say, if actually A2 was less than A1, then we're going to have the following scenario. So you have two different possible scenarios. So you want to go ahead and keep on using it. So a branch in this decision tree is going to be a comparison, and it's going to be giving us a path. So every level is one comparison, but the branch tells us which path we're going to take. Let's go ahead and sort of expand further on this left branch. So right here, we already compared A1, A2. Let's compare A2 and A3. So if A2 is less than A3, well, then we have the following. A1, A2, and A3. And now we can see that, well, if that's the case, well, A1 less than A2, A2 less than A3, we can conclude right now that this list has to be sorted. So the green box really implies a sorted list. Even I'll go ahead and use, I'll go ahead and also box these in as well. So green sort of circle implies that it's a sorted list. So I'll go ahead and I'll just do this that way we don't get confused with the picture. So green implies a sort. So after two comparisons, we already sorted our array. However, we can't always, we're not going to always have this scenario happen to us. So what if, let's say, the opposite happened in this branch? What if we actually have A3 less than A2? Let's say we have this situation. Well, then in that case, we'll have A1, and then of course A3 would come next, then A2. And can we conclude this list as sorted? Well, we actually can't. We know A2 is the biggest element at the very end, so we know A2 is in its correct position, but we don't know about A1 or A3. All we know they're both less than A2, but among A1 and A3, we can't really tell. In this left branch right there, we could tell because by transitive property, we could tell that it was sorted, but here we can't make that call that it's sorted, so it's still not sorted technically. So now we have to do one more comparison to really know for sure if it's sorted. So we're going to have A3 and A1. So if A1 is less than A3, well, in that case, we're going to have A1, A3, and A2. And we can conclude that this list must definitely be sorted. And also likewise, what if the opposite? What if A3 is less than A1? Well, then we have A3, A1, and A2. We just swapped those two values. And in this case, we can conclude that it must be sorted. We know that A2 is the biggest element in the list, A3 is the smallest element in the list, A1 is the middle element. We know that has to be the case, so we're done. We can already safely say we're sorted. So we have a decision tree set up, and then of course these green nodes imply sorted. It's going to be the leaves of this tree. So we have this part worked out, but we still have to process this right side of this tree. So right here we have where A2 was less than A1. Okay, so how about let's keep doing some more comparisons. So in this case, if we took this path, then we compared A2 and A1, but we didn't really compare A1, A3 just yet. Let's compare those ones. So let's go ahead and have the case where, oops, wrong color pen. So let's say we have the case where A1 is less than A3. Then in this situation, we'll have A2, A1, and A3. And at this point, we can safely conclude that this list has to be sorted by transitive property. A3 is the biggest, A1 is the middle, and A2 is the smallest. Based on these results, if we take this path, we can definitely safely conclude that this list must be sorted. If you know, if this and this are both correct, then we know it's got to be sorted if we took this path. So now, well, of course, once again, maybe we're not so lucky that the opposite is the case where actually A3 is less than A1. If that's the case, wait, yeah, so A3 is less than A1, then that just means, or hold on, let's make sure I get this correct. Okay, I think I'm correct. So in this situation, if A1 is bigger, then at this situation, we're going to have basically A2, A1, and A3. So, wait a minute. Oh, my mistake. A1, okay. That looks correct. Okay, I knew I made a mistake there somewhere. Hold on, so A2 comes first, then A1, and then, no, it should be A3 then. My mistake, I'm getting kind of lost here. Hold on, let me just make sure. So if A1 is bigger than A2, A2 is bigger than A1, this is going to be the correct list, okay? And if A1 is bigger than A3, then A1 has to, okay, there we go. That was my mistake. My mistake. There we go. Now we're correct. All right. So in this case, now A1 will go to the back. So in this situation, we have this scenario, we can't really conclude that it's sorted. All we know for sure is that A1 is going to be the biggest element in this list. But A2 and A3, among these two, we don't know which one is the bigger or smaller. So you have to do one more comparison to be 100% sure that we have a sorted list. So now you have to compare A2 and A3. So A2 is less than A3. Then we have A2, A3, and A1. And we can definitely safely say that this is a sorted list. And then likewise, we have the other side. So we have if A3 is less than A2, then A3 would go first, then A2, then A1. And this has to also be sorted. Let me zoom out here so we can see the entire picture. There we are. So now we have this this sort of decision tree. So you have all different types of paths we can choose, but ideally, so this is going to be really the best possible sorting algorithm for any comparison-based sorting because sometimes merge sort and quick sort might do some extra redundant comparisons. This one is not going to. So like in the case where we had that leftmost node where we had sort of this situation right here, we had only two comparisons and we were done because we don't have to do any more comparisons because if this is the case, then we know for sure that our list has to be sorted. So this will do no redundant comparisons. It's really the most efficient possible sorting algorithm. So you want to go ahead and see, well, you want to know what's the most this is going to actually do. So what's the max number of comparisons? So we have 3 comparisons in the worst case. So this very efficient algorithm has to do at least 3 comparisons to really be sorted in the worst case. So the idea here is, well, the height of this tree is going to really tell us exactly the max number of comparisons we have to do. What's the most we're going to have to do in this case? Yeah, it's a decision tree, just a decision tree for, I guess, for comparison-based sorting is probably what I'll call this. So, yeah. And so in this case, the height of this tree is what we want to actually know. So then, first of all, remember, so I guess I sort of didn't really cover this right now. I should have, I guess you did cover binary trees in CS302. So this will be a relatively balanced binary tree. And remember, the number of nodes, log 2 of number of nodes will give you the height. But also, you can guesstimate it if it's a very balanced tree or a relatively balanced tree, then log 2 of the number of leaves are also going to give you a relatively good estimate for the height of a balanced binary tree. So in this case, well, how many leaves do we have? Well, we have 6 of them, as we can count them. So how do we get 6 from our original size of our array, which was 3? Well, okay, 3 times 2, but really it's actually, we can see here, we have every permutation of this list, in our leaves. So we're going to have exactly 3 factorial number of leaves. Or in general, if we had a more larger tree, this decision tree actually, so I guess I'll zoom in on this and I'll zoom back out, so it's easier for writing if I zoom in. But I'll zoom out in a second. So the amount of leaves in the tree is n factorial, where n is going to be your number of elements, number of items in your array, in your decision sort of tree array. So n is your number of elements, so n factorial number of leaves. So then we can just go ahead and just take the log of this, log 2 of n, because we're going to have um, basically we're going to have n factorial leaves, log 2 of n factorial, as we already kind of, I think in that first day I might have explained this, but anyway, this will be actually n log n, or base of log, I guess, just n log n, I guess, in this situation. So height of this tree, okay, fine, I'll say the height of the tree will be O of n log n. That's the height of this tree. So I guess I'll put this here, height of tree. Then I'll zoom out so we can see everything, including these nodes as well. Okay. So what does this really tell us? Well, it tells us that this very efficient algorithm, this super duper efficient algorithm, in the worst case, will take n log n number of comparisons. So this is literally the best algorithm you can possibly come up with for any comparison-based sorting, which means that there is no other comparison-based sorting that could do better than this. So this is our lower bound, which means that any other comparison-based sorting will have to at least do n log n number of steps. So I'll go ahead and I'll just write that here and I'll zoom out again. So let's see it first. This implies that the lower bound for any comparison based sorting is omega n log n. Now it's kind of confusing. We have O of n log n right there, but the height of that decision tree is O of n log n. So in the worst case, it has to do n log n steps. It's a very good algorithm, which means that no other possible sorting algorithm can do fewer than that, because this is the best possible algorithm for sorting. So any other sorting algorithm you can possibly think of, so quick sort, merge sort, any sorting cannot be better than n log n in the worst case. So this really means that no comparison based sorting can run faster than n log n steps in the worst case. So we had insertion sort, which could be O of n, but that was not in the worst case. That was in this best case. So this lower bound really, any lower bound in general really means that in the worst case, you can't do better than this. So lower bound is really like your answer to the question. So that means that, well, we already have several sorting algorithms that are n log n. So which means that sorting has been kind of solved. That's why it's one of those complicated, simple problems, because it's, it might be complicated for someone to come up with. Imagine sort of discovering or constructing quicksort algorithm. It might be a little bit challenging to come up with it. But the idea is that runtime is n log n. So it's a closed problem. So sorting is closed. We can't really improve. So there's, I guess it's kind of like, this lower bound is almost like having a game, a football game or whatever, and you know the answer, you know the results before the game even starts. So it makes the whole game not fun to watch, I guess. It's kind of like that. It's almost like the same idea. Lower bound kind of spoils. It's a spoiler basically. It tells us, well, you can't do better than this. So if you already found something at that same time, well, that means that's the best you can possibly do. So it kind of does seem a little depressing, actually, but, or maybe not. It's actually a good thing. It means it's a closed problem. It's nice to have something closed, I guess, in computer science. So that's basically that. So essentially, lower bound for comparison-based sorting, omega n log n, which means you cannot do better than n log n in the worst case. So maybe I'll put this here as in terms of big O, make it more confusing. So in the worst case, you can't do better than log n. You can't have an O of n in the worst case. That would violate this proof. So you put theta instead. But anyway, that's what this really means. Can't do better than log n in the worst case. I know big O and log n implies anything lower, so you gotta just say theta then. Sure, I'll say theta. That way you can't go below like that. Anyway, so that's pretty much sorting the comparison model. Any questions on that before I go on to our next sort of sorting methods, I guess. So this is kind of like the epilogue where, okay, we already have a spoiler alert, but there's a bonus track on this movie, I guess. There's a bonus track here, so we're not quite done. So there are cases where you can actually have sorting run better than n log n, but it would not be a comparison-based model. So let's go ahead and go over let's go over, I guess, for now. Let's talk about, I guess, bucket sort next. So right now, we're going to be talking about the non-comparison sorting models, which is, I don't know if this was covered in CS 302 or not. I know in my class I don't cover it. I think I was TAing in the past in CS 302 at this university, and it was never covered. So I don't think this was covered, but then again, I don't know every single, I don't know all the instructors who do 302 what they do, but I'm going to go on a limb here and say, well, it might not have been covered. We'll just say that for right now. So bucket sort is going to be a non-comparison based sorting algorithm. So what does that mean to be non-comparison based? Well, that means we're not going to be comparing any two elements in the list. We'll do maybe some type of, well, we're not doing any comparisons actually. We're not quite doing comparisons at all. So there's no comparisons really being done here, which is really bizarre. But there's a reason why we cover these non-comparison, because they do have actually nice runtimes in certain situations. So bucket sort, let's go ahead and sort of write out what is bucket sort. So bucket sort really is, well, we're given an array, I'm going to call it A, I suppose, of size n. So this is actually going to be really the pseudocode. So this portion here is our pseudocode for bucket sort. So you're first given the an array of size n, and then we're going to create an array b of size n as well. and indices will go from 0 to n minus 1, same as they do for the array, the original array. So some other methods I'll do in this class, we may actually start from 1, not from 0, but for now we'll just go ahead and have it start from 0. And then we're going to set each element of B index I as an empty linked list. Could be empty list, but I think empty linked list is more specific. Don't worry, we're not going to be coding linked list here, so I know in my 302 class earlier this semester, that was like a nightmare doing a linked list program. So don't worry, no coding of linked list, just we're going to visualize and imagine a linked list, which is definitely a lot more nicer than actually coding one. So the first step, after we have all this, we want to go ahead and find sort of the biggest number in an array. So find the largest element in the array A. You want to compute its number of digits. So compute its number of digits. And it's pretty simple because if we know the base of the numbers, well then log base of that number, of that largest number, will give us number of digits. So it's number at logarithmic properties. So we take log 10 of a number and take the ceiling of it. It's going to give us the number of digits in the number, basically. So very simple operations. You find the biggest element and compute its number of digits, just so we know that. And then after that, what we're going to do is going to be our main algorithm, our loop in this situation. So we're going to have a for loop. So for I equals 0 to n minus 1, we're going to insert, I'll indent this a little better. We're going to insert an element A index I into this linked list, into B index, I'm going to go ahead and say n times A of I divided by B up to the power D. So I'm going to go ahead and actually just, in this case, number of digits will be D, and B is going to be the base of that number, base of whatever numbers we're using here, and take the floor of these. So this is almost like, kind of like a hash structure. It's almost like, you can almost think of this as a hash sort in a way. So we're not covering hashing in this class, but it kind of creeped in a little bit right there. So we're going to map an element into a bucket. And each bucket, so each element B index I, will be a linked list. So B is going to be an array of linked lists, and we simply have to just insert an element to the back or to the front of the linked list. So we have to map A of I using this sort of function. We take A of I divided by the B up to the power D, multiply it by n, which will map us to a position. And then we're going to insert this node to the front, to the back, doesn't matter where. Just put it somewhere there. So we're going to sort of map all these into these buckets. So I'll do an example, of course, after I cover all of this. Once we have that, then we're going to go, so for I equals 0 to n minus 1, we're going to just sort each B index I bucket, or you can just maybe, it's going to be a linked list, but each linked list is like a bucket basically, hence name bucket sort. So we sort each of these. So each B index I will be its own independent linked list. And we just sort them, I guess, using insertion sort. Why do we choose this insertion sort? Well, it's really the best, simplest sorting algorithm. I'll put a dash here to sort of imply this is going to be the body of that for loop. And then at the end, just simply concatenate. I'm going to try to spell concatenate. coordinate all the elements in B index 0, B index 1, up to B index n minus 1. So a very simple non-comparison based sorting. So there's other ones that are a bit more, how should I say, more complex, but this one's really the simplest one of them all. So bucket sort. Let me go ahead and zoom out so we can see the entire pseudocode. Hopefully I can fit it into one frame. Let's see, I think if I do Control Shift, so this is basically the pseudocode for bucket sort. Hopefully it is still viewable here on WebEx. But basically that's all there is to it. We just have to map every element into this bucket and then simply sort each bucket using insertion sort. And we'll see in a second, well, why insertion sort? Well, it's a good sorting algorithm because it could be all of n in some cases, but the idea is that each bucket will have not many elements in it. So it doesn't really matter which one we pick, but insertion sort's a very nice sort of sorting algorithm. Among all of the quadratic sorts, that one's definitely the better one between that and selection sort and bubble sort. So let's go ahead and show an example here just to get an idea of how bucket sort works. It's really the simplest non-comparison sorting algorithm. So let's go ahead and just draw this up. So I'm going to go ahead and move down here a bit and just zoom back in so make the writing part easier. Let's do an example of bucket sort just to get an idea of how this actually would work. So I'm going to, let's see, I'm going to create maybe a box over here for my original array A. Awesome. And let me set the there's 10 elements here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. So only 9. Alrighty. Now use the red as our indices. I'll have the following arrays, sorry, following elements. So 78, 17, 39, 26, 72, 94, 21, 12, 23, and 68. So this example I sort of borrowed from the MIT book. I guess it's a good idea to use the book as examples, so that way if in case the lecture doesn't make any sense, you can of course look at this problem in the book and maybe it'll give you extra sense. Maybe it'll give you can read it in the book, of course, to get an idea. But this is actually the same problem from the textbook, from the MIT book. So, okay, there's our first step. We have our array. Perfect. So now I'm going to go ahead and create sort of our buckets. Let me go up to my code first, make sure I wrote this out correctly. Yes, you want to create n buckets. Okay, I wrote that there, so that's good. So you have to create 10 buckets because we have 10 elements, so 10 buckets. That's going to be the rule of thumb. This will be our A array, I suppose. I'll put this here as A. And I'm going to create my 10 buckets. I'm going to, I guess, rely on this again. I'm going to try like, do it like this. So we're going to have an array of linked lists. I'm going to zoom out after I finish all of this, but let's go ahead and put my bucket array here. So I've got 10 elements. Hopefully I did this correctly. Ah, darn. If I have to like, so okay, let me go ahead and zoom out so you can see the entire thing so I know how to scale this then. Okay, so 9 lines. Okay. Well, good enough. This is going to be our bucket array, and each of these will be its own independent linked list. So array of linked lists, everyone's favorite data structure in CS 302, array of linked lists. So each of these will be set to null. So I'll go ahead and I'll just put these arrows here to denote that they're all going to be pointers. And for some reason, I always think of this at this level in Sonic when you're, I think it's that Sonic 2, that water level. And Dr. Robotnik has these two columns, these two kind of totem poles, and he hits the top and arrows shoot out. It reminds me of that every single time. So anyway, so here's our initial bucket. And now we're going to basically take every element from A and put it into one of these buckets. So I'm going to zoom out a little bit so we can see it all. So right now, the biggest element in this array will be 94, and it has 2 digits. So we're going to divide every number by 100, multiply it by n, basically, because n will be 10 in this case. So what's going to happen, we first take 78 and divide it by 100, because the biggest number 94 has 2 digits, and we take the base of this, which is base 10, up to the power 2 is 100, divided by 100, then multiply it by 10. So 78 divided by 100 is 0.78, multiply it by 10 will be 7.8, the floor of that will be 7. So 78 will be mapped over here. All right. And then 17, well, 17 divided by 100, which is 0.17, multiplied by 10, will be 1.7. Floor of that will be 1. So 17 goes right there. And 39, well, 39 divided by 100 is 0.39, multiplied by 10 is 3.9. Floor of that will be 3. So we go to index 3 of our bucket array. Then 26 divided by 100, 0.26, multiplied by 10, 2.6. Floor of that will be 2. Insert 26 right there. Next one, 72 divided by 100, 0.72. Multiply it by 10 will give us 7.2. Floor of that will be 7. So insert 72 right there. So insert to the front or to the back, doesn't matter where we insert it, I'll insert to the back. And then 94 divided by 100 is 0.94, multiplied by 10 is 9.4. Floor of that will be 94. And then 21 is the next element in our array. So 21 divided by 100, 0.21, multiplied by 10 is 2.1. Floor of that will be 2. So 21, we insert this right there. And then we have 23 left. So 23 divided by 100, 0.23, multiply it by 10 is 2.3. The floor of that will be just simply 2. So we tack 23 on over there. And the last one, I believe, is 68. 68 divided by 100 is 0.68. Multiply it by 10, 6.8. Floor of that will be 6. Insert into element 6. Hold on. I'm missing something. Where am I missing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 78, 17, 39, 20, 26, 72, 94, 21. Oh, I'm missing 12. Okay, my mistake. So 12, okay, so 12 divided by 100 is 0.12, multiplied by 10, 1.2. So floor of that is 1, so 12 would go over there. My mistake. That should now contain all 10 elements. So we simply use almost like a hash method. We just map each element to an element in this bucket array. So now what we have to do is we have to essentially sort each of these buckets. So we can assume that this will be a doubly linked list. We could assume that a doubly linked list, I know it's a pain to actually code this, but conceptually, a doubly linked list is not much more complicated than really a singly linked list. So we can assume that we have the head and tail pointers for every single linked list in this structure, and we can easily run this insert and sort algorithm. So let's go ahead. I'm going to just simply, whoops, I want to draw that. Let's go ahead and copy this array and show this buckets after we do sorting, after we sort all of these elements. So the nice thing about having one node, I can just go ahead and just copy and paste instead of having to redraw all of this. So in this situation here, after sorting this array, you would obviously have 12 here, and 17 would come over there if you were to insert and sort this. So I'm going to go ahead and just put an arrow here. So after, put this here, maybe in green. After sorting each bucket. And then here we will have 21 would go first, then we have 23, and then 26. 39 is already sorted. It's empty, empty, 68. This one we would sort this, so 72 would go first, then 78. So we have to go through each bucket one by one and just insert and sort each one of them. And we can assume that we'll have a head and tail pointer for each of these nodes, each of these linked lists, and it'll be doubly linked list, so it makes it very simple to kind of move from right to left and insert. But of course, you could also we can also sort it from left to right. It doesn't really matter. But anyway, it's very simple to implement insertion sort for an array, or sorry, for a linked list. So now we have this setup. Now you have to concatenate all the elements together. So let's go ahead. I'm going to copy and sort of copy this list. I'll have to redraw all of this, which is the one benefit of having one node. Let's go ahead and sort of copy this. I'll put it over here. Oh, not quite, but good enough. I guess I can just move this down. So then we have to basically just take the list in our buckets and just basically just concatenate that list. All right, let me go ahead and sort of zoom out so we can see all this. So obviously going through our elements, the first one is 12, so we have 12 first, then 17, then 21, then 23, then 26. We just basically have to go through all these lists one by one, insert them into this A array. Then we have 39 would come next, then 68, then 72, then 78, and then 94. This is going to be our sorted array. This will be, I guess, after concatenating. After concatenation. And there we are. We have our sorted array. So we did some comparisons. So bucket sort is kind of the simplest one. There was some comparison based because we did have to insert and sort each of these buckets, but overall we didn't have to insert and sort the entire array. So bucket sort is kind of like a little hybrid really of how shall we say non-comparison and comparison. I want to start with this one first. This one is definitely the more simpler sorting algorithm for non-comparison based sorting, but that's that. So same example from the book, just so I also can put another note here. So after basically just sort of insert each element from A to B using that method we had earlier. So this is kind of steps we took. So that's how bucket sort of works. Pretty simple to implement if you have to do it like for homework. Nothing really to it actually, but I might ask some other questions on this as well. But anyway, now let's go ahead and go over runtime analysis for bucket sort. So let's zoom in a bit here. And let's go over time complexity analysis. Okay, so the first step is we have to, of course, take all the elements from our original array A, and we have to basically insert them one by one. But first, okay, we first have to find the largest element in the array. So we can do that. So, okay, fine, so let's highlight all these. So the largest element, or I should say find. So find the largest element in the array. Well, that takes O of n time. I mean, no brainers, O of n time to do that. And to compute number of digits of this, so compute the amount of digits for the largest element, well, it's going to essentially be, log of, I guess, I'm going to use k for right now. So k denotes that biggest element. So find largest element k. So k will be that largest element. So it's going to be log base whatever, log base 10, log base whatever of k. So I guess if k is going to be some constant or much less than n, this could be at worst, could be really log of n at worst if k is extremely large, I guess. But either way, this is not going to hurt the runtime. So it's O of n plus O of log of k, where k at most, well, I guess it depends on how big k really is. So I guess if k is rather a decent sized number, this will be rather constant. Let's say if k is a ginormous number, then this could take a while to convert. So we'll assume for now that k will be relatively decent size number. So that's kind of the real bottleneck for these non-comparison based algorithms is the size of these numbers can play a role. But for now, we'll go ahead and just assume that k is a relatively small enough number. Nothing exponential, I guess, is the idea. So it'll be some type of polynomial of n in the worst case. I think then it should be all right. But anyway, we'll just think of it as k will be some constant. So this will be a constant amount of time to do this conversion into finite number digits of this number using that log function. And then, of course, to insert each element into a bucket, well, it's going to take O of n time as well. Go through all the elements one by one of A, and we can do a tail insert or a head insert. So each insertion into that linked list will be constant, and we do this n number of times. So O of n to do that. And now here is like where we have the actual, the kicker, I suppose, here, is now we have to sort or insertion sort each bucket. And for now, we'll leave this kind of open. We'll just kind of not discuss this just yet. We'll leave this part open for right now. It will take whatever time it takes. We'll just leave this open, but we'll come back to this in a second. After we do that insertion of each bucket, then we have to concatenate each element from all of the buckets. So we have to just take all the elements and all our buckets and concatenate them. That'll take O of n time as well. So we add all these parts up, they're all O of n or something less than O of n, or this would be not going to be really worse than n as long as, well, actually, even if the k is a very big exponential value, it could be still actually worst case n in this situation. So anyway, this will also not be worse with n most of the time. So all these operations are all going to be O of n. But the big question mark here is insertion sort of each bucket. So I mean, I'm not really big on statistics really, so I'll just try to kind of sort of explain this by just waving my hands around like so. So the idea is going to be that for a bucket sort, we have, if let's say the numbers are distributed evenly. So if we have a sort of a regular distribution of the items in items in A, in an A array. That means what's going to happen is each bucket will have very small amount of items. And as n gets larger, the number of buckets gets larger as well. So statistically speaking, if we have a regular or normal distribution of our numbers, then each bucket will have really not so many items. A very small fraction of n, not many. You can almost consider it to be relatively constant. So each bucket will take constant time to sort because we're going to have very few elements. I mean, maybe at most, depending on how big n is, but really, as n gets very large, then statistically each bucket will have roughly, at most 5 or so elements in each bucket. So it'll be constant. So that means that the amount of elements in each bucket will be a constant. Should have actually moved this down a little further. I'm going to go ahead and sort of move this down to make some more space. I apologize for note taking. I will post these up anyway, but because I kind of made a mistake, this we move this down a little bit, so I have some space here. So in that case, then each bucket, so each bucket takes O of 1 or constant time to sort, and we have n buckets. So runtime actually will take overall O of n to sort all the buckets. As we can see here, every single component of our pseudocode bucket sort all takes O of n time. Let's go ahead and go over the worst case scenario. If we have, so I don't know what's the right word to use to describe this, but I guess a not regular distribution, whatever that means. So for example, what if, again, I have to move this down again you have to move this down again further, okay. Well, luckily I have one node at my disposal, so I'm lucky. I had last time to move this down, last time, I think. Yeah, it should be last time. So anyway, suppose if we have, let's say, n elements in our array, and they're all going to be 2 digits, but they're all in those 10 to 19 range, then we actually could get all the elements would be in one bucket. It's not normal as long as we have a normal distribution, which typically, so unless there's an adversary who is purposely giving us inputs that are very bad, but of course we can use statistics, we can figure out that all these numbers are all close to each other, that don't even use bucket sort in that case. We can very easily verify the numbers coming in like that. If we have the entire list given to us at once, all at one time, we can verify to see whether different ranges. So we know if they're all kind of clustered in a certain range, okay, then don't run bucket sort at all. But anyway, though, if you do run bucket sort, and we have a very not normal distribution of our keys, then we could have it where each, or a few buckets, I should say, sorry, a few buckets could contain many elements. What I really mean is that, I guess roughly O of n elements, or some fraction of n, but roughly around that linear-ish number of elements, or theta of n will be more exact, but I'll just say O of n for right now. So if we have this many, then insertion sort, we're going to take we're going to have basically a constant number of buckets, but each bucket will have a lot of elements in them. So that means it'll take O of n squared to sort each bucket. So it takes O of n squared to sort each bucket. Now, if we have this situation, then most of the buckets will be empty except for a few. So it'll be a constant times this. So we would only sort a few buckets. Thus, we actually get O of n squared in the situation. So everything is O of n, except this sorting part is the only kind of bottleneck, really, for this algorithm, is that sorting portion. It depends really on distribution of our numbers. So that means in the worst case scenario, in absolute worst case, it could run O of n squared time if we have these numbers not very nicely distributed. We have an adversary that gives us a very bad distribution of input. So 100 numbers, all are in that 10 to 19 range. Then we'd have them all be in one area or something like that. But on average, unless there's an adversary at work, on average, numbers will be relatively randomly or normal distribution of numbers typically, which means that every bucket will have a few elements in them. Of n buckets, each of them will have a few elements, so each sorting will take constant time and O of n. So that really means, in the best case, and even on average, the runtime will be O of n. So let me go ahead and just finalize this here. So in the best and even the average case, it's going to be O of n, bucket sort. But here's a case where now we have an algorithm introduced that in the average case, it'll be O of n. Because remember, for insertion sort, it can run O of n in the best case, but that was in the best case. But on average case, however, insertion sort for n elements is relatively n squared. So, but this is an algorithm right now that in the best case, but also in the typical case, the average case is what we mostly care about. The average case typically is O of n. So we have a situation where we can get an average runtime O of n, which is better than those comparison-based algorithms. But of course, in the worst case, we get O of n squared. But we could very easily detect if we have a very not nice distribution of our numbers, we could probably just, not even run bucket sort in that case, is the idea. So really, it depends on distribution of our elements, and we can verify it easily using some statistical methods. And if we know it's not distributed nicely, we'll then just ixnay on bucket sort, forget it, then do something else. So that means bucket sort, unless we really are not smart about how we use it, if we know that the numbers are distributed nicely, bucket sort will give us O of n for every single instance we use it, if we use it in the right situation. So we just found a better algorithm than n log n, but this is definitely not the comparison model. And we have to create extra, an extra array to do this, our bucket array, and we have to do extra memory we have to use. But doing this, though, we get a better runtime than the comparison algorithm. So we'll cover some more non-comparison algorithms next time. But I guess for right now, we'll go ahead and call it a day. So I guess take care. Have an awesome rest of your day. Stay safe. A great weekend. Thanks for watching, and see you guys next time.